Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. So far, we've treated the first and second derivative tests like a set of instructions. If f prime is positive, the graph goes up. If f double prime is positive, then we have an upward-facing cup. But in mathematics, just because my teacher said so isn't a proof. Why must a positive derivative imply an increasing function? And why does the rate of change of the slope dictate the bend of the curve? Today, we're going to use the mean value theorem, which is one of the most powerful existence theorem in calculus, to prove the fundamental connection between a function's derivative and its visual geometry. Now, before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. This should look familiar to you because we've used it multiple times. We know that if f prime is greater than 0 on an interval, then f is increasing on that interval. And if f prime is less than 0 on an interval, then f is decreasing on that interval. And now we're going to go through the formal proof for the increasing test. Let's first write down what our idea is going to be. So the idea is we're going to pick two arbitrary points. We're going to pick x1 and x2 such that x1 is going to be less than x2. Now, if the function is increasing, what that means is we're going to get f of x1 is going to be less than f of x2. So this is what we want to prove. Let's get started. So we first start by letting x1 and x2 be two numbers within our interval I, such that x1 is less than x2. And those are two arbitrary points that we're picking within that interval. Then, by the mean value theorem, there exists a value c that is within the interval x1, x2, such that f of x2 minus f of x1 over x2 minus x1 is equal to f prime of c. And if we rearrange this equation, we can write this as f of x2 minus f of x1 is equal to f prime of c times x2 minus x1. So what do we know about some of those terms? Well, we know that we picked x2 to be greater than x1. So which means x2 minus x1 is going to be greater than 0. That's the first thing. And then the second thing is we're told that f prime of x is greater than 0 on this entire interval, which means that f prime of c must also be greater than 0 because c is some number that's within this interval. So therefore, because of our 1 and 2, we know that f prime of c times x2 minus x1 must be greater than 0 because we have two positive numbers multiplied together. And since f of x2 minus f of x1 is equal to that, we have f of x2 minus f of x1 is greater than 0. And moving f of x1 over to the right side, we end up with f of x2 is greater than f of x1, which is exactly what we wanted to show. So therefore, we have proved that f is strictly increasing on our interval I. We're not going to be doing the proof for the decreasing test because it would be a very similar process, only with the signs flipped. In fact, we're going to leave it as an exercise at the end of the video to see if you can formally structure a proof. And now we're going to move on to our concavity test. The concavity test says that if f double prime of x is greater than 0 for all x within the interval I, then the graph of f is concave upward on I. And similarly, if it's less than 0, then the graph is concave downward on I. And now we're going to do the proof for part A. Now, if you recall the definition for concave up, the definition says that a graph is concave up on an interval I if the graph lies above all of its tangent lines on the interval I. So here we have our function f, and then we've drawn one particular tangent line at, let's say, this point here, which is k, comma, f of k. And we're going to call this tangent line g. So the idea here is we want to show that f of x is greater than g of x for all x on our interval I. The first thing we're going to do is we're going to write down an equation for g of x. And we're going to do that using our point-slope form. So we get g of x minus the y value of that point, which is f of k, is going to be equal to the slope, which is going to be f prime of k, times x minus k. Now isolating g of x, we get g of x is equal to f prime of k times x minus k plus f of k. And now I'm just going to highlight this because we're going to be using this a little bit later on. Next, we're going to divide up our interval I into two parts. So it's going to be from k to x, and then the other interval is x to k. So you can imagine it being to the right of this point, and then the other segment is to the left of that point. So for the first part, we are going to consider the interval k to x. So since the second derivative exists, we know that f is continuous on this interval and also differentiable, which means by the mean value theorem, there exists a c that is within the interval kx such that f prime of c is equal to f of x minus f of k over x minus k. Now, since we know that f double prime of x is greater than 0, that means f prime of x must be increasing. And this is the increasing test that we had just proved above. Because f double prime of x is just the derivative of f prime of x. So if f prime of x is increasing, then that means f prime of c is greater than f prime of k. And this is because c is greater than k. Next, we're going to replace f prime of c with the right-hand side of that equation. So we get f of x minus f of k over x minus k is greater than f prime of k. Multiplying both sides by x minus k is going to give us f of x minus f of k is greater than f prime of k times x minus k. And finally, we're going to isolate f of x, so we get f of x is greater than f prime of k times x minus k plus f of k. But notice that this is just what we highlighted above, and that's equal to g of x, which means we get f of x is greater than g of x. And then we just need to repeat the process for the other interval, which is from x to k, which we're not going to go through because it's very similar. And once you do that, you're going to get that f of x is also greater than g of x for that interval. So therefore, by the definition of concave up, we have proved that if f double prime of x is greater than 0 for all x within the interval I, then f is concave up on the interval I. And now let's do a quick recap of what we covered in this video. We saw that the mean value theorem is the rigorous link that links slope information at a single point C into value information across an entire interval. So for the first derivative proof, it relies on the fact that if the average slope is positive, the end value must be higher than the starting value. And as for the concavity proof, it relies on the first derivative test being applied to the derivative itself, which says that if the second derivative is greater than 0, then the slopes are increasing, which creates this concave up shape. And now it is your turn to give this a try. Can you use the same logic that we used to prove the increasing test to try and write a formal proof for the decreasing test? And if you want, you can also follow the same logic to construct the proof for the concave down test. Make sure to leave a comment below if you have any questions and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.